Part 2, we're flipping the coil in a B field. So we're going to flip from up to down, from in to out. And so the idea is what we're changing is the orientation. With Faraday's law, you can change the magnetic field, you can change the angle, or you can change the orientation. So in this case, our change in the magnetic flux is the magnetic flux final minus the magnetic flux initial. So for one coil, this would be essentially 2 times the magnetic field times the area, when the magnitude of either up flux or down flux is BA, where B is the magnetic field and A is the area of one loop. We calculate the area of one loop by multiplying pi by the sum of the, that should be a 4. Dividing by the sum of the diameter of the inner layer of inductor plus the outer diameter. If you add that up, you have to divide by 4 and then square. This would effectively produce an average radius. And where do you get that information? You get it inside the inductor coil. There's a little slip of paper there. If you turn it over, you can see. So then the induced EMF is minus the total number of turns times the, 2, is minus 2 times the number of turns times the magnetic field times the area over the change in time. That would produce the current in the coil times the resistance. That would be dq dt. If we divide through by the change in times, the change in the current would be a function of twice basketball NBA divided by the resistance. So with the vertical one, we'll see an upward flip going down, horizontal, in to out, but we've got to align with the compass in the table, so it's strictly as horizontal as we can get it. Okay, then how do we calculate what we need to do to get the numbers? We have to set up a ratio between what happened with the current and what happened with the flip. So in this case, dq over dqc would be the deflections from the flip over the deflections from the coil. That would be equal to 2 times NBA over the mutual inductance times the current in the coil. Doing the algebra, we get the equations for the magnetic field vertical and the magnetic field horizontal. This Ci over dc is the slope we're going to generate using the slope equation. So the B field vertical would be the mutual inductance times that calculated slope times the vertical deflection over 2 times the number of turns times the area of one loop. The B field horizontal would be the mutual inductance times that slope times deflection horizontal over 2NA. So to get the dip angle, a little closer, we would have to take the inverse tangent of the vertical deflection over the horizontal deflection. And then to get B total, we square the B field horizontal, square the B field vertical, take the square root. That would be B total. So when you do this lab, be sure you answer the questions in the book and tell me what the answer, and give me the answers. And remember, how do we create a magnetic, why do we want to do all this stuff? It's because we generate AC current by turning a coil of wire in a magnetic field. And in that case, it wouldn't be a flipping function, it would be a sinusoidal function, which we'll be dealing with in AC current.